Inside the world's longest underwater tunnel, how the $15 billion Impossible Channel tunnel was built, full process. You can see everything inside the video.
For centuries, connecting Britain and France seemed like a fantasy. Napoleon dreamed of it in 1802.
The secret lay deep beneath the seabed, a layer of chalk marl, soft enough to dig, but strong enough to hold.
The plan was ambitious. Not one, but 3 tunnels. 2 for trains and a central lifeline for service and safety.
In 1986, the treaty was signed. The private sector would fund the greatest engineering feat of the 20th century.
Before digging could begin, sonar mapped every inch of the seabed to avoid faults and flooded fissures.
Standard machines weren't enough. They needed 11 massive mechanical earthworms, custom built for the task.
On the British side, work began at Shakespeare Cliff, digging a massive access shaft to lower the machines. In France, at Sangatte, engineers sank a giant concrete shaft straight down to the tunnel level.
Water was the enemy. Massive pumps were installed to combat the constant threat of flooding from the sea above.
Precision was key. A deviation of just a few meters would mean the tunnels would miss each other entirely. Piece by piece, the 1,000-ton tunnel boring machines were lowered into the earth.
These beasts used hydraulic rams to push themselves forward, crushing rock with immense pressure.
The engines roared to life. The first bite into the chalk marked the point of no return. Tungsten teeth chewed through the chalk marl, turning millions of tons of ancient rock into dust. The excavated rock, or spoil, was carried out by endless conveyor belts, faster than trucks ever could. Inch by inch, the British team pushed forward, creating a perfect cylindrical void under the sea.
The French faced tougher, wetter ground. Their machines were sealed like submarines to withstand the water pressure. Deep underground, pilots guided these mechanical leviathans, relying on data screens rather than eyesight.
As the machine advanced, it needed armor. Precast concrete segments were rushed to the front. Robotic arms placed the tunnel lining rings with millimeter precision, sealing the tunnel as it grew.
The machine used the newly built tunnel as a foothold, pushing off the concrete rings to drive forward.
Grout was injected behind the walls, filling every gap and locking the tunnel into the surrounding rock.
The British waste rock wasn't wasted. It was used to build a new piece of land, Samphire Hoe, at the cliff's base.
The smaller service tunnel led the way, acting as a pilot probe to check ground conditions for the main tunnels.
Constant probing ahead ensured they didn't hit a pocket of high-pressure water that could flood the project.
Conditions were hot and humid. Workers toiled in shifts, deep beneath the crushing weight of the English Channel. Every 375 meters, workers dug cross passages by hand, connecting the main tunnels to the safety escape route.
Piston relief ducts were cut to let air pressure escape, preventing the high-speed trains from pushing a wall of air.
Disaster struck often. Unexpected leaks required immediate grouting to stop the sea from breaking in. In the humid mist, lasers were the only eyes. A calculation error here would cost billions.
Once the French hit solid chalk, they switched their machines to open mode, doubling their speed.
Life underground developed its own rhythm. For 8 hours at a time, this concrete tube was their entire world.
At the end of a shift, the man-rider trains ferried exhausted crews back to the surface and fresh air.
The abrasive rock ate steel. Cutter heads had to be inspected and replaced in the cramped space behind the face.
They needed a place for trains to switch tracks. Massive crossover caverns were excavated under the sea.
These caverns were so large they required massive steel arches to hold back the immense weight of the ocean floor.
A mobile concrete factory operated underground, supplying the endless demand for lining and floors. Beneath the tracks, a complex drainage system was laid to catch any seepage or condensation.
As the kilometers ticked by, the two teams, British and French, raced toward each other in the dark.
As they got close, sonic probes were sent forward. They were listening for the rumble of the other machine.
There was no way to reverse the massive British machine. The solution? Steer it down and bury it.
The British machine dug its own grave. It was concreted over, becoming the permanent foundation of the tunnel.
The French machine, however, was dismantled. Piece by piece, it was carried back to France.
Ventilation was critical. Fresh air was pumped miles underground to keep the workforce alive. Fire was the greatest fear. Safety protocols were rigorous, but the risk was always present. Miles of high-pressure water pipes were hung from the ceiling, ready to suppress any blaze. Slowly, the rough excavation was transforming into a clean, smooth concrete tube.
Final measurements confirmed that the structure held its shape against the crushing external pressure.
With the shell complete, the focus shifted to the floor. Tons of steel rebar prepared the way for the tracks.
A perfectly smooth concrete slab was poured, the foundation for the high-speed rails to come.
October 30, 1990. A small probe broke through the rock. For the first time, Britain was connected to Europe.
Through a hole the size of a dinner plate, workers from both nations peered at each other.
The machines were stopped. The final few feet were dug by hand, with pickaxes and sheer excitement.
Graham Fagg and Philippe Cosette made history, the famous handshake that bridged the channel.
Cheers erupted. Flags were swapped. The impossible engineering dream was now a reality. It was the ultimate celebration. Champagne flowed deep beneath the sea.
The world watched. Cameras beamed images of the dusty reunion to millions of living rooms.
The alignment was nearly perfect. The two tunnels met with a deviation of only a few centimeters.
Soon after, the massive rail tunnels followed suit, completing the three-tube connection.
The party ended, and work resumed. Now, they had to turn a hole in the ground into a railway. Specialized construction trains entered, laying thousands of concrete sleepers.
Miles of steel rail were welded into continuous strips to ensure a smooth, silent ride.
25,000 volts would power the trains. Overhead catenary wires were strung along the tunnel roof.
High-speed trains generate immense heat. A massive network of cooling pipes was installed to act as a radiator.
A complex nervous system of signals and sensors was wired up to control traffic safely.
Giant fans at the coast began to turn, pushing a constant breeze of fresh air through the tubes. Heavy blast doors were installed to seal off sections in case of emergency or maintenance.
The darkness was banished. Emergency lighting illuminated the walkway for the first time. Fiber optics and radio cables ensured the trains would never lose contact with control centers. Inspection vehicles slowly rolled through, checking every bolt, every weld, and every wire. The moment of truth. The first test train crept into the portal, testing the clearance.
Engineers watched the pantograph connection closely, ensuring the power supply was stable.
Speed tests began. The train pushed faster and faster, reaching its operational speed of 160 kilometers per hour.
Safety systems were triggered. A mist of water filled a test section, proving the fire suppression worked. The rolling stock arrived, massive Le Shuttle wagons designed to carry cars and buses.
Trial loading began. Trucks and cars drove directly onto the train, a rolling highway.
And the Eurostar, the sleek Greyhound built to sprint between London and Paris.
In the control center, operators simulated the complex dance of trains moving in both directions.
Rescue teams drilled constantly, practicing evacuations into the central service tunnel.
A final polish. The tunnel had to be pristine for its royal unveiling.
May 1994 officially opened the Channel Tunnel.
The monarchs took the first official ride, traveling under the sea, dry and safe.
Commercial service began. Passengers boarded in London and emerged in Paris just hours later.
For drivers, it changed everything. No more ferries. Just drive on, relax, and drive off.
Freight boomed. Goods that took days to ship now arrived in hours.
For every driver, seeing that speck of daylight at the end remains a magical moment.
To understand the scale, you could stack the Eiffel Tower above it, and it would barely break the surface.
The physics of the tunnel breathe. Vents open and clee to manage the pressure of the speeding trains.
Security remains tight. Every vehicle is scanned before entering this critical link.
The work never stops. Every night, crews descend to maintain the tracks while the world sleeps.
Rails are replaced, systems updated. The tunnel is a living organism that needs constant care.
Today, it is the busiest railway line in the world, a pulsating artery of Europe.
Inside, passengers sleep, unaware of the millions of tons of water pressing down above them.
The terminals are bustling hubs, gateways that erase the physical divide of the channel. It didn't just connect two cities. It knit together the entire high-speed rail network of a continent. Above, storms may rage and ferries may dock. Below, the link remains unbreakable and calm.
The machines that built it are gone, but their legacy is cast in concrete and steel.
Day and night, the shuttle weaves its way back and forth, a metronome of modern commerce.
The Channel Tunnel proved that with enough will, engineering can conquer nature's greatest barriers. It is truly the seventh wonder of the modern world, the impossible tunnel that united a continent